All right, so in this video, we're going to be doing something called the Cauchy-Schwarz inequality, which says that if you have a couple vectors, then the absolute value of the dot product is going to be less than or equal to the product of the magnitudes. Okay, so I'm not sure why, but it is possible to justify this using this rule that we learned before. But for some reason, and I don't know what it is off the top of my head, I think that there's some sort of consensus that it's not a fully valid proof for whatever reason, and I've never really understood why. So we're going to try to do it avoiding the angle between the vectors. I found a proof that I thought was interesting because it's definitely within range of the class, but I have no idea how anybody would intuitively come up with this or even think to do even one of the very first steps in the proof. So I figured we'd take a look at it and just kind of, see what you think of it. So let me get rid of this stuff here. Okay, so the Cauchy-Schwarz inequality. So first, we'll take a look at a simple case. What if your first vector was just the zero vector? So if you use the zero vector, well, then we know that u dot v in absolute values is just going to be 0. And we know that the magnitude of u is 0. So if I multiply that by the magnitude of v, I'm going to get 0. And we know that 0 is less than or equal to 0. So our, this thing right here is met. So then we need to look at the case that's going to be more complicated. What if u is not 0? So if u is not the 0 vector, then, all right, so let's take a look at what happens now. And so right off the bat, this is where I don't know why someone would think of this, but we're going to consider the vector little r times u plus v, where r is some real number. It's a scalar. Okay. And then we're going to look at what happens when we take that vector and dot it with itself. So ru plus v dot ru plus v. So if I use some of the dot product distribution properties, so I'll distribute these two to the second parentheses first. So it's ru dot, and then the second vector, ru plus v, plus v dot, and then the second vector, ru plus v. And then I'll distribute the ru to each of these things inside the parentheses, and then do the same thing over here with the v. So this will turn into ru dot ru plus ru dot v. And then over here, this is going to turn into v dot ru plus v dot v. Okay, now if we remember some other dot product properties, there's one that says if you have a constant times a vector dot another vector, that's the same thing as c parentheses a dot b, like that. So over here, if I pull out both r's from the ru dot ru, I'm going to get r squared, and then I'm left with u dot u. And then I'll pull out the r from each of these guys. So this is going to be r u dot v plus r v dot u plus v dot v. And I'm just going to apologize now. Every so often, I think my hand might brush up against the mic, and then I'll go soft. So sorry if that happens. All right. So let's see now. Well, u dot v and v dot u are the same. Dot products are commutative. So this is going to then turn into r squared u dot u plus 2r u dot v plus v dot v. Okay. Another property of dot products is if you take some vector and you dot it by itself, well, that's really the norm squared. So if it's the norm squared, you know it's got to be 0 or bigger. So since that's what we were looking at over here, we know that this is going to have to be greater than or equal to 0, right? So it's, well, I'll just leave it like that. Okay, well, this thing right here on the right side of this inequality, the greater than or equal to 0, that thing is really a quadratic expression. So it's a quadratic where the variable is r, and our a, b, and c, a is really u dot u, which is a scalar, b is 2u dot v, and c is v dot v. Now if you have a quadratic, let me shrink this down so that this will fit better. Give me 1 second here. Okay, so if you have a quadratic that's always 0 or bigger, and you were to graph this thing, so if it were quadratic in terms of x's, in this case it's in terms of r's. But if you have a quadratic that's always 0 or bigger, then if it was always bigger than 0, then it's got to always be above the in this case r axis. And if it was ever equal to 0 but only one time and the rest of the time it was positive, then you get something that looks like that, where it just grazes the axis one time. So that means that this quadratic, so here I'll write it out. Since our quadratic is greater than or equal to 0, it can only have zero roots or one root. Right? It can never be negative. The quadratic part can never be negative, so you can never end up with 2 roots there. So not 2 roots. Okay. Well, the way that you can kind of see when you get 0 roots or 1 roots is if you look at the quadratic formula. Now in this case it would be r equals, not x equals. It'd be negative b plus or minus square root b squared minus 4ac all over 2a. The part that tells you how many solutions you get for this is the part inside the square root. That's called the discriminant, if you remember. So the discriminant, if I have 0 roots, then the discriminant, 0 real roots basically, then the discriminant is going to have to be a negative number, because then I have a negative underneath the root. I don't get any real solutions. If the discriminant is 0, then this root essentially turns into nothing, and I'm just left with one answer, negative b over 2a. And if the discriminant's positive, that's when you get 2 different answers. So if we look at the discriminant b squared minus 4ac, well, I know that I need 0 or 1 root. So the way that happens, I get 0 roots if it's negative, and I get 1 root if it happens to equal 0. So we know the discriminant has to be less than or equal to 0. So let's take our a, b, and c and plug those into the discriminant and set it so that it's less than or equal to 0. So if we do that, we've got 2 u dot v all squared minus 4 u dot u is a, and then c is v dot v, is less than or equal to 0. So if I multiply out this thing, that's going to be 4 u dot v squared minus 4, and then u dot u is really the magnitude of u squared, and v dot v is the magnitude of v squared, is less than or equal to 0. I could divide both sides of the inequality by 4, so the 4's go away. And then I could move the negative u squared v squared magnitudes over to the right side, and I'll end up with this line, u dot v all squared is less than or equal to magnitude of u squared, magnitude of v squared. So then what I'm going to do is I'm going to take the square root of both sides. So if I do that, square root of u dot v squared is less than or equal to square root of magnitude u squared, magnitude v squared. Well, the square root of something squared is really like a fancy way of saying absolute value. So this thing is going to turn into the absolute value of u dot v is less than or equal to the absolute value of the magnitude of u times the magnitude of v. Well, magnitudes have to be 0 or bigger anyway, so that means that these absolute values aren't necessary, and that leaves us with the Cauchy-Schwarz inequality. I'm showing it to you because I've seen it crop up in various advanced math courses, so it's useful to have seen it, and it's obtainable with what we know, so I think it's just kind of a useful thing to present in the class. Later on, I won't assign this yet, but later on it turns out you can use the Cauchy-Schwarz inequality to prove this guy right here. So we'll eventually do that one together. Okay, so I hope that helps a little bit. It's definitely kind of a creative looking proof as far as I can tell. I never would have thought to create this vector and then somehow involve quadratics and use the discriminant, but somewhere somebody thought of it, so all right then. All right, so I'll see you guys later.